momentum of the photon going that will be hf2 divided by c. But now the electron has been given a kick, so it has motion, it has velocity v, so it will have a momentum mv. It's the definition of momentum, right? The mass times the velocity. But this time it's a relativistic mass. It includes the rest mass, right? So you've got the momentum of the photon heading that way, and plus the momentum of the electron heading to the right. Okay, so mv. So here's a second equation. So the conservation energy equation, call that equation 1. Conservation of momentum equation, call that equation 2. Right, and we will use these. All right. Now have a look at equation 2, and we'll start doing some from now on, it's just algebra, right? It's not the physics goes out of it. It just becomes a manipulating formulas algebraically. All right. Okay. So have a look at equation 2. This c underneath on both sides, multiply both sides by c. So you get a c up here. So you get mvc. Take this term hf2 over the other side, and then square the whole thing. So you'll get mvc all squared. Here it is here. Now this goes over the other. The hf2 goes over to the other side. So you'll get h into f1 plus f2, right? And then squaring the whole thing. So h squared f1 plus f2 all squared. I hope you can see that. You just take this over, and you get this, and then square the whole thing. So expanding this out, so f1 plus f2 all squared gives you, s squared plus 2f1 f2 plus f squared, right? So it's just algebra, all right? So that resulting equation, call it equation 3, because we're going to use it later, all right? Now from equation 1, that's this one here. Take this over, take this hf2 term over, and then square everything. Square both sides. So you get m squared c to the 4th, here it is here, right? You're squaring this, m squared c to the 4th. You'll get h into f1 minus f2 plus m naught c squared, and the whole thing's squared. Right? This whole thing is then squared because you squared that. Alright, now we'll expand this out. You just take the square of it, so you get h squared f1 minus f2 all squared, which gives you this. You'll get 2 times this, so 2m naught c squared h f1 minus f2, and then this all squared. So m naught squared c to the 4th, right? That's just algebra. That equation we will use again, so call it equation 4. Alright. Now subtract equation 3, this one, subtract it from equation 4, this one. And why do you do that? It works. That's the usual answer, right? Okay, maybe not obvious, but well, that's how you get Nobel Prizes, right? By doing non-obvious things that have big impact. All right. So 4 minus 3, this equation minus this equation, gives you m squared c to the 4th minus this one, m squared v squared c squared. So this minus this will be all this minus all that. Right? So the f1 squared, f2 squareds, they all cancel. I've skipped a line or two. You do it at home. You calculate it for yourself. So you think, after cancelling stuff out, you're left with this expression: minus 4h squared f1 f2 plus 2mc c squared h f1 minus f2 plus m naught squared c to the 4th. Right? Now here SRT special relativity theory. There's a formula for the mass when it's moving. So if your rest mass, the mass a particle has when it's not moving, is m0. 0 means its velocity is 0. Okay? So that's the so-called rest mass. The mass the particle has when it is at rest, meaning not moving. Okay? m0. So you divide that by square root of 1 minus v squared over c squared. Okay? So as v, that's a famous formula in special relativity theory. This relation between m when the particle's moving and m0 when it is not moving. Now you can just see here from the algebra, as v, the velocity of this particle, as it gets close to c, then v squared over c squared is almost 1. Okay? So 1 minus something almost 1 is very small value. So that means m here becomes very large. Okay? So the closer you get to the speed of light, this m here can become huge, right? And that's what's happening at the LHC, the Large Hadron Collider. These protons are accelerated so fast, their velocity is getting very, very close to c, so the mass of these protons is enormous. I mean, well, in less than a decade, they will be up to, once LHC is up to full speed, full capacity, it will be up to 14, I think, GeV, giga, billion electron volt energy. So you can calculate what the mass of the proton is just using general special relativity formula. Okay, all right. So you have this formula. That's just from knowledge of special relativity theory. So if you square both sides and then take this square root squared over, so you'll get m squared into 1 minus v squared over c squared equals m0 squared. Right? You've got that. And we will use this. Right? So we'll use 4 minus 3, and we'll also use this. Okay. All right. So that's question 5 now. That's equation 5, and 5 is the result of equation 4 minus equation 3. So equation 5 now is m squared c to the 4th minus m squared v squared c squared, and that's here. Now these two terms have something in common, namely m squared c to the 4th. So take that outside, and now inside the brackets you'll be left with 1 minus v squared over c squared. Okay. So now here you've got m squared times 1 minus v squared over c squared, which is here, which is just this term here. So instead substitute m0 c squared, the square of the rest mass, m0 c squared. So so for this m squared and this term here, just substitute it for m0 c squared. All right. Okay, so we now have, instead of this, we can put that. But look, we've got the same term on the right-hand side. So cancel those. So this term here and this term just cancel because this is equal to that. And we have the same on left-hand side, right-hand side. So cancel that. And that means that this is equal to that. Right? So 4h squared f1 f2 equals 2m0 c squared h f1 minus f2. That's here. Right? Now we can cancel the 2. We've got an h. Cancel that. Divide both sides by f1 f2, and you'll be left with 2h divided by c. Bring it underneath. The m0, bring it underneath, so you get 2h over cm0 equals, leave one of the c's here because we're going to need it. Now remember you divided by this, so you'll get 1 over f2 minus 1 over f1. But c over the frequency, speed of light is the frequency times the wavelength. So the wavelength is c over f. Okay? The wavelength is speed of light divided by the frequency, c over f. C over f. So this is lambda 2 minus lambda 1, the difference in the wavelengths. and you are asked to show that that difference is 2h over cm naught, 2h cm naught. So we've done it. Okay. Now from about there onwards, it's just, well, except for this, it's mostly just algebra. Right? So a bit of physics from here, and this whole question, you need you need to understand special relativity, and if you haven't done it, then just hang around for a while and study my special relativity course using this text. Oh, which is free on email if you want it electronically. Otherwise, you can get it secondhand on Amazon, but for a price. If you want it in paper, you pay. If you want it free in electronic form, with all its inconvenience, I mean, then you get the glare of having to read it on an e-reader, but it's getting better all the time. My longer term prediction is that the paper publishers sooner or later will die, because the technology, keeps improving. The electronic form of information is costs virtually nothing to distribute it. So the costs, other than the initial cost of writing the book, somebody's got to write it, and the author would like to get some money back. But the price of an electronic book should be virtually zero, because it's spread over the whole planet. And even if you're just paying a penny, a cent or something for your book, with billions of people, that's still quite a bit of money for the author. So things should be arranged